All right, so we are going to continue, ya shabab, the discussion today on the self-contained bearings. And just to remind you that these kind of bearings are designed in a way to operate without the need for any kind of automated lubrication and cooling, I mean, for the lubricant. So the story goes like this. The heat will be generated due to the friction, and then it will be dissipated to the environment. Now, if you recall the problem that we started last class, we have been given the dimensions of the journal diameter as well as the bushing. And from that, we estimated or we calculated this minimum clearance, C, okay? And then using the equation, which is P equal to the weight divided by LD, okay? Using this equation, we calculated the pressure, and by calculating the pressure, we were able to express the Sommerfeld number, characteristic number, as a function of the viscosity, correct? Now, then what did we say? We said that we need to calculate how much power measured in horsepower, okay, is generated by friction. And we said that this is calculated as WNC divided by 1050 multiplied by FR over C. This is a very well-known dimensionless factor. And we calculated this number, like here. We multiplied it by this, FR over C. This is in horsepower. But in order to express it as a heat rate, we multiplied we multiplied it to get the heat generated, okay? Heat generated as 2545 multiplied by HP friction. And what did we get? We got a number, which is again a function of FR over C, but it's measured in BTU per hour. Now, if this is the generated heat, okay, then we can also find the heat loss. And the heat loss was calculated using this function, which is HCR. HCR, we said that this is a coefficient for the heat transfer coefficient for both convection and radiation, multiplied by the area, then divided by alpha plus 1, multiplied by T bar F minus T infinity. Now, we got this one here as again in BTU. We said that we need to do trial and error. That's what we said. And we started by a random number, T bar F, the temperature, the average temperature of the film. And then we started with 190 degrees Fahrenheit. Now, once we know the temperature, TF, okay, then this is the temperature of the fluid in there. And then we can go to the curve, knowing the temperature, and from oil SAE20, we can get the viscosity. When we get the viscosity, we apply it in here. So this is the viscosity. When we get the viscosity, remember that S number is a function of viscosity. There you go, which means you can calculate S number. The S characteristic number can be used knowing L over D to find what? RF over C, which is right there. There you go. We got that. Now, when you get RF over C, you can get the generated heat. correct? And because you assume TF bar over here, you can get the heat loss. Now, when I get the heat generated like this and the heat loss like this, I am done. I got the two values. So why would anybody tell me go and do a trial and error? Why there is another trial? By the way, look, down, we did another trial by assuming that the temperature T bar F equals to 195, which again led you to finding mu prime, then calculating S, then calculating or finding FR over C, and then calculating the generated heat, and then calculating the heat loss. What am I after, Shabab? When am I going to stop? I can do this forever. What should I do? You forgot why we are doing trial and error. We just keep doing it forever.
To get an optimal value. I mean, we stop when we feel like the value is satisfactory.
When?
Maybe when the generated equal to the losses.
Yes, that's right. We will stop when the heat generated is equals to the heat loss. Because this bearing is designed that way. It's a self-contained bearing. And in that type of bearings, the heat generated should be equal to the heat loss. And once is that done, I want to know the other values, the other characteristics. So these two, look, this is 49.5, this is 45. Things got really red over here. So let me just ease it up. After one trial, we got 45 and 49.5. The second trial, we got 44.4 and 46.9. Not too bad. So what did we do? The solution went on trying again and again. And then it turns out, of course, this is, I am adding here two curves, one for the mu ren, which is the viscosity, and the other one for RF over C, lines for the two trial. Okay. Now, the book went on and discovered that at a temperature TF bar, which is equal to 193.4 degrees Fahrenheit, the two generated heat and loss become the same. And the value is 46.3 BTU hours. Yeah, which means I'm done. I got the equilibrium now. Now, by knowing this temperature, find the mu prime. When I find the mu prime, I can find S. When I find S, I can find R over F, RF over C, and so on. There is no trial and error. I just go and find them for this particular temperature. Now, when I find this temperature, I can also go to this curve by knowing S and knowing L over D. I can go ahead, look, and use figure 12 for 24 to find the temperature rise dimensionless variable. What is this variable in PSI? It is this. So this value over here is 9.7 multiplied by delta TF divided by PSI. Why? Because when I get this number, which is around 4 point something, I can multiply it by the pressure, divide it by 9.7, and get delta F. Delta F is the temperature rise? How much the film temperature went up? Okay, now if I do this, then this is delta F, which came out to be 11 degrees Fahrenheit. Now, I know that if you remember, we said that the fluid will get in with T1. This is the oil inlet temperature here. I'm bringing it to you, which is the same as TS. Then if you take that, that temperature supposed to be equal to T bar F, which is the average temperature of the film, minus delta T divided by 2, the average increase, the average rise in the temperature. Why? Because in here, the film temperature has already went up. By how much? By this average. So I take that off from it, and I get the inlet temperature. So the inlet temperature is 187.5 degrees Fahrenheit. Yeah, and remember, ya shabab, this look, from this, the temperature going out to the swamp, okay, is equal to T1 plus delta T divided by 2. This is the temperature. In reality, this is the temperature of the film, the average one. So if you want to find this T1, you need to take this here. You need to subtract it. Now, how about Tmax? Well, we know that as the fluid go in that little region, pressure increase, temperature increase, friction, and then it get out with high temperature. That's the whole problem here. The whole problem is that in that little tiny region, this is where the heat is generated. Now, the oil will take it out. That much is Tmax. That's the outlet temperature, which is T1, the inlet temperature, plus how much did you add in, which is there. Look at it. It is T1 plus delta T. So T1 plus delta T is equal to 198.5 degrees Fahrenheit. Good. Now, we can go back to the equation. Now, the question might ask us a lot. Like, for example, what is the temperature of the surface of the bearing? You know now what is happening in that little tiny thin film? The temperature of the bearing surface, how much is it? Well, we know that equation. I just need to warn you about one little correction, which is in here, that this is a bar here. There's a missing bar. This is the average film temperature, T bar F, plus alpha multiplied by T infinity, which is the environment temperature or the surrounding temperature divided by 1 plus alpha. We know that this is 193. Why? This is the T bar F after trying the error, right? And then we know that the surrounding temperature is 70. We know that alpha is 1, and we got a temperature of the bearing surface 131.5 degrees Fahrenheit. Amazing. Really. This is very nice. I mean, if everything goes well, you can imagine that you bring a temperature thermometer and then or a thermocouple, you stick it on the surface of the bearing and you measure the temperature, and you should expect it to be around that temperature. From a little tiny knowledge about a little tiny space there in the film. Now, we know the S number. We can go ahead from the curve, find H0 over C. Why? Because if you know the S number, you know L over D, you can easily find that ratio. When you find that ratio, H0 over C, because we know C, we can multiply it by C. And what is the result? Is H0. Because the question was asking us, what is the minimum thickness, film thickness, which is H0? There it is. What is the friction? Okay, again, we know the S number, we know L over D, so we can get RF over C, and then RF over C, we multiply it by C, we divide it by R, and we get F. That is the friction. What is the parasitic, friction, which is the friction torque, basically? It is T, which is FWR, and this is equal to this much, 1.28. Now, there is a little extension of this question you may think about, which is, how are we doing here? Is this okay or not? Well, you will see this in another example that we are going to solve. Sometimes they would ask you, can you compare these findings to come on. Yeah, Templar. Yeah, I got the name. So, can you compare this to Templar design criteria? So let's go back a little bit. Just bear with me. A lot of figures. Yeah, over here. So Templar's design criteria, basically, we have 3 of them. The first one, the H0. Now, if you know the diameter of the journal, you can plug it in this equation and calculate this number and check if H0 is greater than this number. If it is greater than this number, then you are okay. If not, then you say, no, we're not okay. We are not following the Templar design criteria. Another thing is the temperature. The temperature should be kept, of the oil, should be kept below 250. I think we were below this. We are around 198 something. So we are good. What is the other one? Is the pressure, the starting unit load pressure, which is this. Now, in this, BST, which is equal to W divided by LD, you will calculate this pressure. And then what do? You will see in some other example, maybe. We know that this is supposed to be less than 300 PSI based on Templar. So one of the ways to have a measure for a design factor ND is to say, I will divide the 300 divided by PST, which is what you have. And you will see how much, because 300 is like your cap, and you will see how much is your condition, okay? Then you divide this by that, and you get a sense of how far are you from the recommended value. And you'll get a number. Is it 1.5? Is it 2? And you can say that Templar said the design factor should be 2. So in another sense, you can imagine that everything here has to be around 2 times the recommended value, less than by the recommended value by 2 times in order to be safe twice, okay? Twice means, like the factor of safety. So now we are going to move on to another topic. We're not going to spend too much time on it, but we'll talk about clearance, and then we'll talk about a pressure-fed bearings. Now, since the beginning, whenever we talked about journal bearing, we told you that temperature is a problem, and most of the time we need to supply the oil, the lubricant, using an auxiliary system like a pump and a coolant, and then we push the oil, we take it out and bring it back. So this is what we are going to talk about in the last part of the lecture today. But now we want to talk about clearance. Now, if you recall, we said that clearance is among the independent variables which designer can control. So you can actually request the machine shop to make the clearances based, like they machine the journal, make sure that the journal has a clearance of this much, that much, in order to contain that clearance. But in reality, clearance is like this common problem that we face a lot in our life, which is when somebody tell you that this is a moving target. I mean, let me spend 1 minute here. A moving target, Shabab, is like when you have this in there and you are standing right there, and everybody would imagine that you can walk to reach here. But if you try to walk and the target itself is moving, when are you going to reach it? Either you have to be faster or you have to find a way to stop that target. Now, I don't want to divert from the topic of the lecture, but I want to tell you that a moving target concept is very important in our life. It's like for education, for health, anything, entertainment. I mean, students and many people say, oh, I've been doing my best, I never succeeded. Maybe your target is moving. How it moves? So a moving target is a dilemma. You need to be faster or you need to find a way to stop it. You stop the target and then you hit it. But if the target is moving, you're probably never gonna reach it. Or it will exhaust you. You keep running, but the target is moving. You think you are there, but you end up being far a bit. So a clearance is a moving target. Why? Because it turns out that you can request the machine shop to manufacture the journal. Maybe you have a control in the journal. Maybe the bearing, you bought it from the manufacturer, but the journal, you can machine it. So maybe you can control that, maybe. But with time, particles get in, wear happen, and then that clearance start to get a bit bigger. Now, so what should you do? And I'm not going to make this too long, but here we have a graph out of an experiment conducted on a set of bearings, and basically by measuring these variables. Look, the temperature, H0, Q, and H. Okay, each one has a curve. And as you see, this is the radial clearance. And as the clearance goes up, things change. So for example, if the clearance is too tight, you will have a spike in the temperature. But if you make the clearance a bit smaller, bigger, the temperature will decrease. Because that area become a little bit bigger, things doesn't get squished. Okay, and same thing, the heat changes, the flow rate of the lubricant, and H0 weirdly goes up and then it drops down. So what the recommendation is that you want an optimal value. And the recommendation is always to start a little bit to the left. A little bit to the left. Now, so you don't just go here because the temperature is too little and so on. No, because this is gonna grow and grow, and then you will reach to an end where things doesn't function or falls into an unrecommended values. So the recommendation is to start here, and then you should expect that with time, the condition of your journal bearing is gonna shift to the right as this clearance increases. Okay, things are measured in microns here and very small. So we have here two tables, one of them for a recommended, okay, maximum, minimum, and an average clearance. Okay, and what we have here is also some calculated analysis on a bearing with a journal size of 1.5 inches, SAE 20, oil, with this temperature, load, length, and R, and speed. And you see that the clearance, as the clearance increases, you know, the we have a temperature drop, it changes, friction changes, Q changes, and the heat changes as well. So this is just an analysis to show you that the clearance, as it changes, things change with it. So this may put you in a little bit of a challenge on knowing exactly what's going on in the bearing after some time. But this is something to be aware of. Okay, these are the same table, but in millimeter in SI unit. Also, we have the idea that there is, as the temperature, whether due to the clearance or due to the operation, the temperature itself, it is expected to change the characteristic of the oil. And in some situation, okay, there are situations, ya shabab, where the lower limit, look, this is a diagram putting 2 bounds, okay, with respect to life in hours and temperature for an oil, set of oils, where so the lower limit is for an oil containing antioxidant over there. And when oxygen supply is unlimited, as you know, this is an oil. Things can dissolve into oil and then change their characteristic. There is also, the life would be affected not only by the presence of oxygen, it will also be affected by the presence of crystals. These crystals might come from the changes in the temperature and they form inside the film. So this is something to tell you that there are more things that change with time, okay, with respect to oil, depending on the operating condition. So you need to be aware of the fact that is this oil will change its characteristics if there is supply of oxygen or not. This is just an example, okay? Now, with respect to the pressure fed bearings, what are we going to do, basically? First of all, the concept here is very simple. You discover that there are possibilities in some situations that this film, this little tiny film, the temperature might reach to a limit which is beyond the recommended value. The swamp, the container, everything around might be at normal temperature, but remember, oil passes through that, and then if the oil loses its characteristic, then you will end up basically damaging the entire volume here. And of course, when you lose the characteristic, whether it is viscosity or other, then there might be overheating or friction or something which will damage the whole bearing. So one of the ways to control the temperature is to push the liquid with a certain rate, which is a flow, which means that you need to pump it. And then when you accelerate this feeding, you will dramatically, you will drop the temperature of the oil. So what will happen is this. You can imagine that this is the journal over here. All what we need to do, if this is the bearing, is to introduce a groove. And in this groove, you will take the oil using a pump and pushing it through. The oil, due to the pressure from the other side, will be sucked up, okay, pushed to the SOM. Then the temperature here can be dropped using a cooling system, then pushed again. Very simple, right? Now, the question that we need to ask ourselves is, how is this going to change the calculation? What we did before, just a minute ago, can apply to a pressure fed bearing. So how is that going to change? Well, what you should know is that in the past, what we had is a bearing like this. This is the bushing, right? We used to say that this is the bushing and this one is the length, right? That's what he used to say. And then the oil will circulate within and everything. Heat loss equal to heat generated, and that's it. Now in here, to introduce the feeding, we have to make that cut. Look at it. So that cut the bearings like into two small ones. And we ended up having a length L prime for each side. And now we can actually study this part like a little bearing alone. The same will happen to the other one. And then what you will see that once we change that L to L prime, things will change. Yeah. So the pressure which is generated now is going to have an equation W over 4L prime multiplied by R. Instead of before, we used to have it as W over 2R. LD, the diameter is equals to twice is the radius. So we have 2R here, we have 4R, because the weight is kind of being divided between two. So that's why we have to put the weight W over 2. What is L prime? It is basically the entire length minus the width of the groove divided by 2. Sometimes it's given to you. Sometimes the width is given to you, so you use this equation to calculate the L prime. You will also see that whenever we have all of the equations that we worked out before, where L is present, things will change. We'll have, for example, this is the distribution of the velocity, U, right? And you see here, we have L prime. In reality, what will happen is, just to make it easy for you, and in order to save time, and without going into the hassle of the derivation, what are we going to do? I'm putting this table for you, which compares the naturally circulating oil system, which is self-contained bearing, and then we have a pressure-fed lubrication system. And as you see over here, this is the velocity distribution equation. This, you have seen it like now a week or something ago. And here, the derivation for the same, which is the distribution of the force, but with an L prime, with a pressure fed. There is a pressure being fed into the system. Now, of course, there's not only L prime, there is S here, which is the pressure now. We are pushing it with the pressure. So same thing, we have a QS measured from the table here. QS is measured using an equation logically, because we know how much is the pressure and the flow rate will be affected by that pressure. The unit load, this is it, as we discussed before. The temperature rise, as we showed you earlier, we got it from the table, from the dimensionless temperature rise variable. Here, the temperature rise in degrees Celsius and degrees Fahrenheit is given to us as an equation. Yeah, same thing, the heat loss. This is, I think you remember this equation, we just spoke about it a minute ago. And here we have an equation for the heat loss, where again, there is an effect of the temperature that we just measured, the flow rate which we calculated over here, and so on. For the chart, all the chart that Raymondi and Royd made for us, we used to have L over D as to determine which curve should we use. In this case, we will use, instead of L over D, we will go and use the curve for L prime over D. Okay, L prime over D. Now, Before I talk about this, ya shabab, I want you to remember one thing, and I don't mean to be like bushy, like a push on this a lot and a lot, but it's worth reminding you about it. I mean, can you imagine that if anybody who tells you everything you study here should be thrown in the garbage, and then you talk to him and tell him, show me how do we pick a journal bearing, I am pretty much confident that he will show you the curves for Raymondi and Royd. He'll tell you, look, you don't need KFUBM. You don't need them. You just need to find the characteristic number using this equation and find R over F and so on and so on. You may have curves, ya shabab, from other manufacturer, which has a different characteristic number. Yeah. But essentially everything is the same. It's just different numbers, different unit, different size, but then you reach the same conclusion. And from where did we get those numbers? Raymondi and Royd spent tons of hours probably trying to juggle this Reynolds equation, unsolvable equation. It's not unsolvable, by the way. It's not solvable analytically. So I want you to think about Reynolds. Reynolds, ya shabab, he's a scientist, said, listen, I know what people want. They don't want math. They don't want differential equation. But put this aside. Let's do it right. So he matched up the physics and math together. Of course, if you make the fancy equation, but it doesn't describe the physics, then it's wrong. It's wrong. But so you don't insist on the math. You insist on getting both the math and the physics together. So what happened? He did that. He said, listen, this is how it is. We can't make it simpler. You know, there are things in life, we can't make them simpler, ya shabab. Not everything, ya shabab, is 1 + 1 equals to 2. It's just, so he did it. And then these guys said this, so I say, okay, this is not the first time engineers and scientists faced up with an equation which is analytically unsolvable. So said we can solve it numerically, and then they generated the curves. And can you imagine solving these problems, getting the details about the temperature of the surface of the bearing from connected to the temperature of that little 0.00 something inch film of an oil at an RPM which is 30 revolution per second of an oil which 20 whatever. I think this is amazing. Just remember that very well. Remember that very, very well. So here, what are we going to do? We're not going to solve this problem. We'll not have time to do so. But I want to introduce the problem to you. It says here, we have a circumferential groove pressure-fed bearing is lubricated with SAE grade 20. So this is the grade of the oil, which means whenever we look into the viscosity curve, we look at the curve for SAE 20. The oil is supplied at a gauge pressure of 30 psi. That's the pressure by which we are pushing the oil. The journal diameter is 1.75 inches, okay? And the unilateral tolerance is minus 0.002. The inches. The central circumferential bushing has a diameter dB for the bushing, which is 1.753, and a unilateral clearance of 0.004. The L prime over D ratio is 1/2, and it says here that the angular speed of the journal is 3,000 revolution per minute, which is an equivalent of 50 revolution per second. The radial steady load, this is W, which is equal to 900 pound force. Okay, the external sum is maintained at 120 degrees Fahrenheit, as long as the necessary heat transfer does not exceed 800 BTU per hour. We want to find the steady state average film temperature. We want to find H0, Tmax, BST, and then compare them with Templar criteria. We want to estimate the volumetric side flow rate QS, the heat loss, and the parasitic friction torque. Now, just to introduce you to this problem, if we know the diameter of the journal, we can divide it by 2 to get the radius of the journal. We will use this. Then the minimum clearance is the diameter of the bushing minimum minus the diameter of the journal maximum. And then what do we get? We get divided by 2, which is going to give you this clearance, 0.0015 inches. Now, L prime over D is equal to 1 over 2, which means that L prime is equal to D over 2, which is the same as R. Correct? So this L prime is the same as R. If we know this, then we say, okay, what about the pressure? The pressure, we said, this is forced pressure, not natural. So P is going to be equal to W over 4 R L prime. You should not use P equals to W over 2 R L.
Doctor, L prime or L square?
L prime, yeah, I think. Don't know why I did that. L prime. So you should not use this one. This is for naturally cooled bearing. And once you get the pressure, as you see, we get the pressure, then again, we are in the same story. Same story. We get S as a function of the viscosity, and then we can follow. I stopped here with the other class, so I will have to stop here with you, but you should expect the same, except knowing which equations do you use. They are a little bit different, okay? So this should be easy, inshallah. It's not a big deal.